Now, I would like to move on to our discussion on the polyphase decomposition, which we had already described. I would like to pick it up from there and then move forward and develop that further. Okay, so the polyphase decomposition we introduced in the last lecture. Let me give a little bit of background to it, since this is the first time we are formally introducing it. Because it is polyphase decomposition, probably the result that really opened the doors for multi-rate signal processing to come into widespread use, was first introduced by a French researcher. His name is Maurice Bélanger, which in the year 1976. Okay, so that was probably the opening point, and his observation of multi-rate and polyphase was in a completely different context, but we have translated it into our notation. So, maybe at some point some of you who are interested should take a look at Bélanger's original paper and try to see why he used the term polyphase. Maybe a hint to that is what is the magnitude response of this element? Unity, all pass filter, right. It is a Z inverse is an all pass filter, but it has got a phase. Okay. Now, Z minus 2 also an all pass, it has got only phase. Okay. So, basically he was looking or thinking about some mechanism by which he will translate a filter into sub filters which have got these components, okay, effectively Z inverse, Z minus 2, Z minus 3, which is nothing but the polyphase decomposition and the polyphase. So, that is where it is coming from, but he came about it in a very different way, and of course, as in all inventions or discoveries, the original person thought of it in a very different way, but then we are able to give interpretations that are interesting. And so, the example that we looked at in the last lecture, if you have a filter H of Z, summation n equal to minus infinity to infinity H of n Z power minus n, we said that we would write it as two summations n equal to minus infinity to infinity H of 2n, grouping all the even coefficients or the even powers of Z, Z power minus 2n, plus then the odd terms. I will factor out a Z inverse, which then says I get n equal to minus infinity to infinity H of 2n plus 1 Z power minus 2n, that additional. So, you can see how the polyphase, in this case just another term with just another phase, is emerging, and this is what we introduced in the last class. We called this as E naught of Z squared, we call this as E1 of Z squared. Right, that is what we said, and of course, if you had to apply the polyphase decomposition along with the downsampling, we showed how the structure could be utilized. Now, if you remember, we left the discussion with a task to apply the polyphase decomposition for the upsampling case. So, maybe we just write that down just for completeness sake. Okay, so H of Z is being written as either E naught or H naught, does not matter, polyphase components of this form. So, this structure can be rewritten as upsampling by a factor of 3, implementing this structure. This would be called a parallel form implementation of a digital filter. So, whenever you have a filter which has been written as some terms that are added together, then it is a parallel form implementation. So, H naught of Z cubed in parallel with Z inverse H1 of Z cubed in parallel with Z minus 2 of H2 of Z cubed, and all of these terms will get added together. Okay. Now, this type of structure we are going to see again and again and again. So, this writing these plus signs so many times is actually quite cumbersome. So, what we would like to do is actually introduce a notation which makes it simpler for us. So, what we are going to do is this notation I think you are familiar with from digital filters. What that means is that signal is getting split into two branches. The same signal is traversing on the two branches. Now, on the output side, so if I have two signals which come like this, it is an adder. In multirate structures we often do the following. This is also an adder. Okay, so you do not have to keep drawing this plus signs. So, this structure could be written in the following form with the proper arrows. That means the two lower branches get added and then they add to the top branch. So, these are this portion and this are identical. So, again rather than keeping adding those multiple times, we will do that. Okay. So, now of course, we would like to use the noble identities, but before that this structure can be rewritten as instead of Z inverse H1 of Z cubed, interchange the order. Those are two linear blocks. So, upsampling by a factor of 3 using the convention, this is H naught of Z cubed, the lower branch is H1 of Z cubed followed by Z inverse signals to be added, and then the other branch is H2 of Z cubed followed by Z power minus 2, and this signal also to be added. So, please draw the arrows. Once you draw the arrows, you can interpret them correctly, which way the signal is flowing, which signal is getting added, which two signals are getting added at each point. And this is also a node on which the signal just splits into multiple branches. Okay. Now, upsampler inside of the where the signal splitting occurs, you can see that there is a opportunity for us to apply the noble identities. The upsampling followed by filtering, where the filtering is has got a power Z to the power L, where L is the upsampling factor. So, using that we now have the following structure. You have H naught of Z followed by the upsampler 3. The second branch has got H1 of Z and there is a Z inverse. I can move it past the H1 of Z cube, but I cannot move the upsampler past the Z inverse. So, this is upsampled by a factor of 3 followed by a delay. So, the delay I am going to capture it on the output branch Z inverse, okay. And of course, the third branch is H2 of Z followed by upsampler followed by Z power minus 2. So, already there is a Z power minus 1 on the other branch. So, I will just add a Z power minus 1 onto this, and please draw the arrows in the right direction, so that we know which way the signal is flowing, and this is the efficient, probably the most efficient implementation that we can get of this upsampling interpolation filter. And of course, this portion of it is a multiplexer. Okay. Multiplexer with the arm going in the anti-clockwise direction. So, this is a multiplexer operation. So, in other words, what it says is take the data, take input x of n, filter it by sub filters, just like you would do an LTI system, interpolate them, right, I mean filter them, convolution, and then multiplex the data, and that is the most efficient, because you are not doing any operations on 0 valued samples. All of these 0 valued samples and their effect on the structure is actually taken up into the multiplexer. So, there is a efficient implementation that is available to us. Okay. So, now we go back to our discussion. What is the most general form of the polyphase decomposition? General form of polyphase decomposition, we actually refer to two types of polyphase decomposition, and they may seem very similar, but there is a reason why they are. So, we call this as type 1. Most of the time, 95% of the time when we talk about polyphase decomposition, we are talking about type 1 polyphase decomposition. Type 1 polyphase decomposition says take your filter Z transform and split it into summations. So, n equal to minus infinity to infinity h of n m z power minus n m. So, I am taking all the mth coefficients in the first summation. The second summation will be z inverse summation n equal to minus infinity to infinity h of n m plus 1, all of them offset from the mth position by 1 unit of time, z power minus m n. Okay, please note or z power n m. Okay, next is a summation with z power minus 2 summation n equal to minus infinity to infinity, n equal to minus infinity to infinity. This would be h of n m plus 2 z power n m. Okay, and so on. The number of sub computations will be, since you divide to split it up in the multiples of m, there will be total of m. The last one will be a summation n equal to minus infinity to infinity h of n m plus m minus 1. That is the last of the, when you do the subsequences. This will be z power minus n m still with a leading polyphase term. Okay, this will be plus z power minus m minus 1. Okay, so, notice that you have power of 0, power of minus 1, minus 2, minus m minus 1. So, these are, so if you were to label these sub filters in the following way, we can write down h of z as summation L is equal to 0 to m minus 1, basically summation of m sub polynomials, z minus L E L z power m, where E L of z is defined as summation n equal to minus infinity to infinity h of n m plus L z power minus m n. I think I wrote the wrong one. This should be an n m z power minus n. Please be careful about the definition and no confusions, because when it is z power m it is different, but now this is the definition of the polyphase component. We refer to this as the subfilters or as the polyphase components themselves. Basically what this says is whenever there is a structure that introduces these polyphase decomposition blocks, then we have a efficient way of implementing them. Again, we have just now looked at a case where m equal to 2, we saw a case when L equal to 3. Of course, you can see that there is a generalization that is easily possible. Now, I would like to introduce the second version, which is not used as frequently, which is the type 2 polyphase decomposition. So, it is useful for us to just keep that in mind, and occasionally when we use it, I will highlight it to you that it is a type 2 representation. Type 2 polyphase decomposition, again it is for certain introducing certain symmetries in the structures. So, notationally it is exactly the same. So, I take a polynomial h of z, split it into sub polynomials exactly like before. L is equal to 0 to m minus 1, z power minus L, and then the sub polynomials. If I write it as E L z power m, this is type 1, this is type 1. Now, type 2 is summation L equal to 0 to m minus 1, I am writing them side by side so that you will see the difference, z power minus m minus 1 minus L times R L z power m. This is type 2. Okay. So, what are the range of the polyphase components? It can go all the way from z power 0, z power minus 1 to z power minus m minus 1 in both type 1 and type 2. So, which means that E L and R L are one and they are basically the same sub polynomials, but they have been indexed differently. So, that is the only difference, and the result and that observation can be actually captured by comparing these two. You can write down the fact that R L of Z is nothing but E of m minus 1 minus L of Z. Okay, and now probably the question that's on your mind is, what is the reason for even introducing the type 2 polyphase decomposition, and I will answer that when we start looking at the structures, and it will become easy obvious why we have to do, why we saw that. Now before we go any further, I would like to maybe just draw a type 2 filter implementation just for visualization, and again the reasons for using type 2 will become apparent once we start doing that. So I would like to do the following: upsample by a factor of L followed by H of Z. Okay, you may say, well, just now didn't we do this? Yes, we did it with type 1 polyphase decomposition. Please do type 2 polyphase decomposition. Type 2 polyphase decomposition, again I will not go through all the steps. What you would get is R naught of Z, second branch R1 of Z, the Lth branch is R L minus 1 of Z, then the upsampling factors, upsampling by L in each of those branches. There are total of L branches, and here is where the difference comes. Previously the arrows were pointing upwards towards the summation. Now because R naught has got Z power m minus 1, so which means that the delay units are still there, but the arrows are now pointing downward. So this gets added to this, followed by another delay chain dot dot dot, and then the last one comes with a Z inverse dot. So notice that the arrows are downward on the on the branch on this side, and if I changed the order of the multiplexer, of course this happens. So basically it just says that the commutator arm is rotating in the different direction compared to previously, but this is a form that results when I use type 2 instead of type 1. Okay. So now you can see why type 2 has been introduced is so that you can avoid having advanced elements if you want at the structure, because if you had advanced operations, then what would happen? These would have to go in the upward branch, in the upward direction. Now you can now see that there is a way to use that, but again it will become apparent when we start looking at more of these structures. So for now I hope the definition of type 2 is clear, and then the implementation of a filtering operation with type 2, and this is something that once you are comfortable with this, we can build on. But as I mentioned, type 1 is the predominant structure that we are going to be working with. So here is the computational advantage of using the polyphase structure. Okay, computational advantage. So I want to look at the simplest case where I have H of Z followed by a downsampling by a factor of 2. Okay. Now what is the benefits of using polyphase decomposition versus the direct form? Okay. So polyphase, so the comparison is between polyphase structure versus the direct form. The direct form is a form that you would have looked at. Basically it is a combination of delay elements, multipliers, and then the adder. So let us take the case that H of Z is a filter, FIR filter of length 2n. This is the length of the FIR filter. So which means that there will be 2n minus 1 delay elements and 2n multipliers. So the implementation of the direct form would be, first multiplier is H naught, input goes through a delay element, second multiplier is H1, delay element, multiplier H2 dot dot dot, the last one comes through a delay element Z inverse and gets multiplied by H of 2n minus 1. Okay. Now these are the, and all of these signals have to be added together. This is the direct form implementation. Okay. I am sure you would have studied this in basic DSP. So this is the direct form implementation of the filter alone but then I also have to have the downsampling by a factor of 2. So, in the direct form I can of course move the downsampling to the other side, but you know what, really doesn't help much, because I end up having to compute the multiplication. So, let us look at how many computations I am doing per output. So, number of computations per output sample, computations per output sample. So, think of it as a hardware implementation, you are counting in a hardware implementation where the first block is doing the direct form filtering, and then the second block is doing your sampling, downsampling. So, computations per output. So, this is the step 1 or block 1. Block 1, at every clock cycle, what is the computation that is happening? Block 1, every clock cycle there will be 2n multiplies, you agree with that? All the filter coefficients will multiply whatever is there in their input register. 2m multiplies, how many adds? 2 element adders, there will be 2n minus 1 adders. It effectively, that is like the last 2 get added and then the previous one and the previous one. So, there will be 2n minus 1 2 input adders. So, this is at every clock cycle, right, and then but you are looking at computations per output sample. Block 2 says compute, throw away one sample, keep that. So, basically this 2n multiplies plus 2n minus 1 adds into 2 is the number of computations per output sample. Basically, I computed twice, the block 1 would have done 2 computations, block 2 says throw away one of those, keep one. So, effectively at the output side this into 2. Now, had you done it using the polyphase structure, what would have been the implementation? It would have been a demultiplexer at the input side, right. So, basically you would have done a polyphase E0 of Z, the odd stream, the even stream would go to this side, even stream will go here, the odd stream goes on the lower branch, that will be E1 of Z. Now, E0 of Z has how many taps? N taps, because H of Z has got 2n, I have split into 2 polyphase components, this has got length is n. So, this one also has got n length. So, these two have to be added, output of these two get added at every instant of time, and that is the output. So, per output sample, number of computations per output sample, like to do that. Each of these blocks basically requires n multiplies plus n minus 1 adds. There are 2 of them, and then there is one more add at the output, right. So, this but the one that kind of scales with the length of the filter is the first term. So, this is the output. Now, if you actually, and this is the output per output sample, and if you compare the two, you will see that there is roughly a factor of savings is 2, savings 2. Okay. Now, if you are doing this for downsampling by a factor of m, this would become a savings of m. And of course, you can show that the same is true when if you are doing the upsampling as well. So, the advantages of the polyphase implementation actually come through very strongly once you are in the domain of the hardware implementations. Now, what we would like to do next is, having given the broad framework, we now would like to talk about the filter banks. And for this, I would request you to start reading a little bit ahead, because this is a part that is actually interesting, easily understood, and so it is helpful for us. So, filter banks is the topic that we are going to be looking at. Filter banks is nothing but splitting a signal through a set of filters. So, application such as your graphic equalizer in the stereo that you listen to, it splits it into high pass, low pass and medium frequencies, and then boosts or so that is a filter bank, basically that is what it is doing. So, example would be a graphic equalizer. So, filter banks come in various forms and very useful, very powerful tool that we get from the multirate side. For in this context, please read Oppenheim and Schaefer chapter 7, chapter 4, sections 7.3 to 7.6. That is the part where it actually covers the multirate, the noble identities, polyphase decomposition and gets into filter banks. Also look at P.P. Vaidyanathan's book Multirate Signal Processing. There it is chapter 4.1, section 1 to section 3. Again, these are the parts that we are going to be looking at. It builds up a framework, as I told you, which is a very powerful framework extensively used in communications. As you can see, every time you do an FFT, you are actually doing a filter bank operation. So, that is the power of this. We will build and develop this in the next class. Thank you.